All right, so this video is going to be all about spring potential energy. So we just got done talking about spring force, or at least hopefully you've watched that video before watching this one, but just a quick recap. Spring force, or Hooke's law, right, is dependent upon K, the spring constant, and X, the change in length of the spring from rest length, right? So we have that Hooke's law equation, Fs equals Kx. As a reminder, you're going to see it with a negative. Usually, I usually don't include that negative because I find that it confuses students. So what that negative means is it just tells us that the spring force, or the force that the spring exerts on the object, is oppositely directed to the displacement of the spring. So for instance, if we were to compress the spring to the right of its unstretched length, or rather stretch the spring to the right of its unstretched length, that force acts left. And if we compress the spring to the left, that force acts right. So that's what that negative represents. That's why I don't really include it. I find it confuses students. So let's jump into spring potential energy. Okay. So here I have a setup A, B, and C. At A, the block is at rest, and we are at our spring compression or spring stretch, or not stretched or compressed. At B, we use a hand or some external force to compress the spring and hold the block at rest. And then at C, we finally release the block and allow the block to move without friction back towards and even past that rest length. So first question is there some net work done on the block-only system from A to B? Now this is where it's important to keep in mind that work, in addition to being like force times displacement, also represents a change in kinetic energy. So at A, my initial velocity is 0. At B, my velocity is 0. So if there's no change in velocity, then there's no change in kinetic energy, so there's no net work done. Okay. Now there might have been work done from A to B, but overall during the entire trip, there is no net work done. Okay. So then we have the same question, but now from B to C. So I've released the block. I have no longer pushing or pulling on the block, and only the spring is allowed to act. So from B to C, there is work done on the block-only system because the force of the spring is external. So we have some work done by the spring on the block. And we also know that because the block speeds up, there's going to be a change in kinetic energy. So we know then that the work equation could be calculated by doing F d cosine theta. So if I was to find the work done by the spring, I would need to do the spring force times the displacement times the cosine theta. So if I think about it, the displacement's fairly easy. That's this way. That's my displacement. Or actually, it would be of the block, so probably a little bit more like that. Okay. And for the first part, F and D are in the same direction. That's why I put a cosine of 0 there. Okay. But I start to see some issues when I think about after I pass this x equals 0, my spring force is now this way, which means the angle between the spring force and the displacement is now 180. So that angle is not constant over the displacement. Also, if I remember, the spring force is equal to kx. As the spring uncompresses, I'm heading back towards equilibrium, right, which is right here. And at that equilibrium, that's where my spring force is 0. So my spring force is actually decreasing over the displacement. So because my spring force is not constant over the displacement, and I have that issue with the angle, I can't use this equation. Okay. So that's where it becomes really helpful to graph, because the graph is going to help show us how the spring force changes with that compression. Okay. So we could graph spring force versus x, or Fs versus x, and I have 2 points labeled, or rather 1 point labeled, right, where it takes a force F to compress the spring x max. Now this graph is a line because the spring force and the compression have a direct relationship, and I know from my reference table, a direct relationship should give me a line. As with any graph, we're going to TSA the graph. So the title here is spring force versus X. My slope would be change in spring force over X. My area would be spring force times X. Now those equations might not ring bells, but hopefully the units do. So the slope would be in newtons divided by meters. And we just learned that that is the unit for spring constant. So the slope here should actually represent K, the spring constant. And the area has units of newtons times meters. Now we might not remember this, but I think it's on the front of our reference table, that a newton times meter and a joule are the same thing. So hopefully you recognize that the area here is the work done by the spring. Okay? Much like the area between any force and displacement graph is work done by that force. So the work done by the spring is going to equal the area, or 1/2 base times height. For the triangle I shaded in, the base would be x max, and the height would be F. Now I know that that F, the force needed to compress the spring that far, is also equal to the spring constant times x max. So I could plug that in, get 1/2 x max times k times x max, which simplifies to 1/2 k x squared. So the work done by the spring can be calculated with 1/2 kx squared. And that's true whether I have a graph or just a regular spring. So that's kind of the shortcut. We just derived the equation for the work done by a spring. So that means the work by the spring on the block-only system is 1/2 kx squared. So how might our system change if we are in the block spring system? So hopefully it makes sense to you that now that we have the block spring system, that spring force is internal and therefore cannot do any work. And the benefit of having an internal force, other than like the Newton's third law canceling type things, is that we can now store potential energy with that force. So because we're dealing with the spring force, we can now store spring potential energy. We saw with the work done by force of gravity and gravitational potential energy that those two values are equal. So work done by internal forces is equal to the change in potential energies. So the work done by the spring on the block is going to equal the energy stored between the spring and the block. Or in this case, 1/2 kx squared is going to equal US, where US is the spring or elastic potential energy. Okay. Elastic is kind of the generic term for anything that stretches or compresses and returns back to its original shape. So think rubber bands, springs, anything along those lines, even diving boards. So we just derived an equation for the spring potential energy, and we'll add that to our reference table tomorrow. All right, so let's say we have a scenario where I have a block that compresses a spring to location A, compresses the spring 0.1 meters. Spring has a spring constant of 100 newtons per meter. The block is not attached to the spring, so it can be released at some point. The dashed line vertically represents rest length, and of course we have no friction. So we have a couple of different locations along. We have A, where we are at rest completely compressed, B, somewhere in between, C is at rest length, D is just along the horizontal surface, E is partway up an incline, and then F is at the maximum height. Now if I think about this block at various locations, right, I here would have like a normal force, force of gravity, and a spring force. Here I'm going to be released from the spring, so normal force and force of gravity. Here I'm going to have a force of gravity and a normal force. Now I know the normal force can't do work, so I can kind of ignore that, but I know that the spring force and the force of gravity could do work. So I don't really want to deal with work because that gets complicated. So what I want to do is I want to include those forces in my system so that I can conserve energy. So we are going to define our system as the block spring earth system. And we are going to ask ourselves what type of mechanical energy exists. So essentially, if I was to give you a bunch of Legos, say 16 Legos, how would you build your bars? Or how many bars would you have at each of those locations? And what types of energies do those bars represent? Okay. So pause, take a minute to figure out what type or types of energies do I have at A, B, C, D, E, and F. So hopefully you pause because I'm going to show you the answers. So at A, we are at rest and our spring is compressed. So we're all spring potential. At B, we are not at rest anymore, so there is some kinetic, and we're not back to our rest length, so there is some spring potential. At C, we are back at our rest length, so the X in the spring potential equation would equal 0. So we have all kinetic at C. At D, we also have all kinetic. At E, we have some kinetic and some gravitational potential because I'm heading up a hill. And then at F, I'm going to be all potential because my speed is 0 at that maximum height. And not like a projectile where we do still have some horizontal velocity. Here, we are truly at rest. Now, because I defined my system so well, we're going to have conservation of mechanical energy because there are no other forces that could do work. If there was friction, we would certainly have work done, and I couldn't put all those equal signs you see there. So then the next thing I would like you to do is try to calculate the speed at location D. So that's after we've released from the spring. So pause and calculate the speed at location D. Hopefully you paused because I am going to show you the answer. You should get the square root of 0.5 or 0.7 meters per second. Now, the best way to do this is to not use forces in kinematics because our force is not constant from A to C, and therefore the acceleration is not constant from A to C. Things get complicated to find the speed at C, which would be equal to the speed at D. So the best way to do this is to use energy conservation, right? This is another time where conservation of energy makes this more convenient. So we would set the spring potential at A equal to the kinetic energy at D, right? We have the spring constant, it was 100. We have the X, it was 0.1. The mass was 2. And again, we just have to find D, VD. So next, if I was to ask you to find the maximum height, so go ahead and think for a couple of minutes, how could you find the maximum height? So there are a bunch of ways to find the maximum height. We could set the potential energy at F equal to the spring potential energy at A, or we could set potential at F equal to the kinetic at D, or the potential at F equal to the kinetic at C, because I know all of that information. And if I know the energy at A, then I know the energy at any other location, and vice versa. That works backwards too. I could ask, or give you rather, the maximum height and ask you to find the initial compression, and you could work backwards from F to A. So you now have enough information to go through and do some practice with spring force and spring potential energy.